You practice. Jody Ruben.
Oh, hey.
Halo Jody.
Yeah, we are.
Hi, Sup.
Oh, Judy speaking, I think. Let me type. Hello, Judy. This is weird, man. Like there are some kind of glitch, yeah, like here as well. I can see the glitch. And look at the presentation; it's happening. Yeah, I'll try to launch from Firefox and see. Well, yesterday we were doing Edge. Edge was fine.
Edge. Oh yeah, it's Microsoft.
Mas Wijanarko.
Ya.
Sambil kita nunggu teman-teman yang lain ngumpul, masih sekitar 4 menit lagi ya, boleh nggak ditampilin di di screen-nya yang kita punya competition buat profesional, Mas?
Oh, oke. Ya.
Sambil nunggu aja sih. Speaker sih sebetulnya udah ready, cuma tinggal nunggu start aja.
Okay. Let me share the screen. Benar yang ini kan, Mbak?
Ya, betul.
Oke. Bagi yang tertarik untuk join?
Ya.
Kan, ya.
Info sebentar aja ya. Jadi Gameloft itu sekarang sebetulnya lagi jalan sih student competition. Jadi kita lagi jalan siswa dan mahasiswa dari sekitar 25 universitas dan sekolah menengah atas dan kejuruan. Nah, kita lagi ada kompetisi buat game development. Ini yang student competition. Nah, yang sekarang ditampilin di sini, ini kita lagi mau ngajak teman-teman profesional nih. Jadi yang memang mungkin sudah punya pengalaman kerja atau mungkin pernah punya project komersial dan lain-lain bisa join di kompetisinya kita. Gitu. Kompetisinya lebih simple sebetulnya, walaupun di situ ada tulisan research, tapi itu adalah semacam mini research. Jadi nggak perlu waktu yang lama, karena researchnya pun juga lebih kepada ini ya teknik juga gitu. Jadi nggak banyak tulisan dan lain-lain yang harusnya di situ. Nah, detailnya nanti kita akan informasikan waktu kick-off meeting. Jadi, sekedar bocoran dulu, memang ada subjeknya ada 2, OpenGL sama C++ optimization, tapi jangan takut dulu sama kata-kata research, ini benar-benar mini research doang yang waktunya bisa dikerjain cuma sebentar. Gitu.
Ya, menarik.
Ya, Mas jangan lupa kalau mau join boleh loh. Siapapun yang ada di sini, selama memang dia sudah profesional, pernah punya pengalaman kerja atau pernah mengerjakan proyek secara komersil, boleh join di sini. Gitu. Itu aja informasinya, Mas. Titik ini nanti ya.
Okay, this is good. This is better. Right.
All right.
Yeah, this is better, man.
All right.
Okay, 1 minute.
All right, you could try to talk.
Hello. Okay. Hello. 1, 2, 3. Test,
Yep.
test. Entity component system in theory. First in theory and then in practice.
Yeah.
We have some causes.
Okay, we're good.
Okay, so yeah.
Oh, the camera. Turn off the camera.
Okay, maybe we can start the event. Okay, I will talk with bahasa as well. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi teman-teman yang ada di sini. Terima kasih sudah meluangkan waktunya untuk hadir untuk acara meetup ya bulanan biasanya dari komunitas Indonesian C++ Programming Language Community atau IDC PLC. Ya mungkin ada beberapa teman-teman di sini yang sudah join tim IDC PLC, mungkin ada yang belum. Bisa di search di Telegram. Ya, saya sendiri sebagai moderator dan host untuk acara ini. Nama saya Wijanarko. Pak Wijaya bisa minta tolong nanti di admin ya, kalau ada peserta. Ya, kembali lagi, maaf. Nama saya Wijanarko, selaku host untuk acara ini. Dan nanti akan ada 2 pembicara dari Gameloft. Yang pertama ada Mas Flo Sebastian yang lead di Gameloft, dan ada Pratius, dia seorang game programmer juga di Gameloft. Mungkin teman-teman di sini ada yang background-nya bukan dari bidang game atau lebih general seperti IT. Ya, di game sendiri mungkin ada beberapa teknis yang berbeda. Jadi nanti di meetup hari ini akan membawakan materi tentang data oriented design di game development, yang mana itu di luar, di beberapa game studio di luar itu sudah banyak yang menerapkan, dan di Indonesia juga beberapa sudah ada. Dan ya, nanti akan detailnya akan saya serahkan ke Mas Flo dan timnya. Terus lebih spesifik untuk membahas arsitektur entity component system. Apa itu entity component system, nanti mungkin bisa dilihat dari materinya Mas Flo dan teman-teman dan tim. Dan ya, di sini kita bisa lihat ada Mas Flo dan Pratius. Hai.
Hello.
Hello.
Okay.
Yeah, Mas Flo and team, the stage is yours.
Oh iya, oke, terima kasih buat kesempatannya. Oke, sorry. Terima kasih buat kesempatannya. Jadi pertama mungkin dulu ya, saya Flo Sebastian sebagai game programmer trainer di Gameloft Indonesia, dan yang di sebelah saya Pratius yang merupakan game programmer juga. Nah, nanti kami akan sharing soal ECS ya, dan nanti kami bagi dalam 2 hal. Yang pertama teori mengenai ECS, yang kedua mengenai prakteknya. Jadi nanti kami akan kasih beberapa contoh mungkin ya, nanti kalau waktunya masih cukup. Lalu nanti untuk teman-teman yang mau tanya, kami udah sediakan Slido ya. Nanti saya akan share link Slido-nya. Jadi buat teman-teman yang mau tanya langsung bisa lewat Slido. Nanti setelah akhir dari presentasi kami akan coba jawab satu persatu dari konten Slido. Ya, mungkin bisa dicatat dari Slido ID-nya 73971 ya di slido.com. Lalu kami juga menyediakan merchandise ya buat teman-teman sekalian yang join, jadi semuanya dapat merchandise seperti ini, notebook ya dari Gameloft Indonesia 20 anniversary. Jadi semuanya dapat. Caranya untuk mendapatkan nanti kami akan sediakan form untuk kalian semua mengisi alamat ya. Jadi yang join di sini bisa ngisi alamat, nanti kami akan kirimkan notebook cantik ini ke alamat masing-masing. Nah, itu dari saya, dan juga tadi juga udah diperlihatkan ya bahwa Gameloft Indonesia juga sedang mengadakan kompetisi untuk riset ya. Dengan tema OpenGLES dan C++ Optimization. Jadi buat teman-teman yang tertarik join bisa join, dan hadiahnya cukup menarik juga di sini. Bisa dilihat di posternya nanti. Mungkin untuk supaya nggak berlama-lama ya bisa dimulai, dan nanti presentasinya akan dibawakan oleh Pratius terlebih dahulu menggunakan bahasa Inggris. Jadi ya bisa diperhatikan secara seksama ya gitu. Dan nanti akan share screen juga gitu. Oke, bisa dimulai. Oke, so Pratius, you could start the presentation.
All right, let me share. Let me share the screen. All right, I hope everyone can see. Yeah, all good.
All good.
All right. So, this talk will basically be about entity component system, and how we have structured the talk today is sort of in two parts. So first part is going to be more theoretical, and the second one will get to see more how the code itself works and how it looks in practice. And also we'll be taking care of that side of the argument. First of all, I would like to thank everyone who made it to the presentation today, and a morning presentation basically. So, all right, let us get on with the talk. So, before starting to talk about what entity component system is, we need to establish what kind of problem we have currently that we have to solve. To formulate the problem would first give us a good solid grounding into what entity component system can help us to solve. So the problem could generally be chopped up into three parts. The first one would be that as we are programming in a sufficiently large code base, we generally come to crossroads with a very complex code base, which becomes harder to read the larger it grows. We have incorporated into it many different features that come as a package with the modern C++ paradigms, and all of this combined together grew to make the problem, the code base, more complex. The second thing is that as we, in almost every programming, in every application, every program that we code, one of the main criteria that we have to look at always is that performance needs to be of a certain acceptable value. It should not cross a certain threshold. And since we program with our current paradigms, we are stuck with we're stuck in a sort of a bubble where we code something and make it so complex that in order to find out where the performance problems are coming from, how do we solve them, it starts to go bad. So it kind of goes hand in hand, the complexity as well as the performance. And the third one as well, like maintainability. As the project grows larger, it becomes harder to maintain because there are basically more than two hands that are coding the same code base in a large application. To give it a more granular view of what might be causing these three issues in modern C++, in modern programming, basically modern programming paradigms. Well, one of the things we usually do is use exceptions, but in real-time high-performance applications, using exceptions that come packaged with the C runtime library, it's not a viable solution because there are certain overheads that come pre-packaged with it, and it is almost never acceptable. And a lot of generally talking about video games, real-time applications don't use exception handling, which come directly from the C runtime library. Projects generally implement their own versions of these. So in order to make it more viable, usually asserts. Templates, although not harmful in a sense of runtime performance, it does hide what the data is. When you're using templates, there's this new paradigm of metaprogramming where templates are used for generating code at run, rather than generating code, doing calculations at compile time, rather than doing it dynamically at runtime. So with this new paradigm, we are able to do certain calculations that we could only do in runtime in compile time, which does improve the performance, but at the cost of readability. The readability of the code base becomes exponentially higher. The book that started the whole metaprogramming movement, the modern C++ design by Alexandrescu, it's pretty hard to pronounce his name. Yeah, even he himself says that although this is a new frontier for him, it does make the code base very, very difficult to read. So we have this other issue. And then we have multiple inheritance. When our classes have inherited deep enough, it sort of hides the data that we have through the upper generations from whatever we have inherited, whatever that derived class has inherited. It hides the data when we look into that class. We cannot get in front of us, like instantly, we cannot reason about exactly the data that is being contained within that inheritance, how deep it is. We have to do a lot of manual checking, and to be honest, in a time constrained environment where we have deadlines, not everyone is going to map out the whole inheritance levels for everything, right? Virtual functions, almost always a bad idea when performance is very critical. So in critical sections of the code base, if you use virtual functions, and so let's say we have an interface class with a bunch of virtual functions, and a class inheriting from it has implemented these virtual functions, and an instance of which we have created in at runtime. Then as soon as, at the moment we create the instance, the constructor will be creating a dispatch table for those functions which are virtual. And every call to that function will now have to be routed through these dispatch tables, also called vtables. And that has another overhead on top of it, right? So we have many issues, as you can see. We have also STL, which is with templates, because it's generally trying to solve a generic problem, and the problem is never the software platform we're using. It's always the hardware we're targeting to. That is the issue here. Because when we try to solve a problem for a generic form of hardware for a larger code base, for a larger set of hardwares, we are missing. We do not pay attention to the parameters we have, the hardware parameters that we have to target to in order to reach maximum performance. So we will just solve it as quick as possible, while also disregarding the performance at the same time. Right? Contributes to hard to read and debug code. I mean, it is. I do agree that it is necessary in certain places to make a code base to code faster, but at the same time, performance critical areas, we need to take care of what we do in those sections. And if these sounded from something we are used to called object-oriented programming or object-oriented paradigm, right? What basically this boils down to is that we are breaking down a problem we are trying to solve, that we are trying to program, that we are trying to into our conceptual view of the world. Right? We create objects as classes, and these classes or objects are reflections of our concept, our abstraction of the problem. That is the solution. If the problem becomes our abstraction, the solution that we use to solve that problem itself becomes a mirror of the world as we view it or as we conceptualize it. These are the classes, and yes, it is easy to reason. It is easy to reason with those kind of things, and it is easy to code the solution if we view our problem and solution as such. So we have for example, we have a design document, how we need to design this application or this video game. And our solution, our way to code it becomes one-to-one copy of this design document into the code base. But the problem therein lies that the hardware does not reason the same way. The hardware does not think in conceptual terms, in human terms. It deals with data. It does not deal with our conceptual view, our solution. So we need not target to, we should not be targeting our solution to our view, rather to the hardware. And the bastion of object-oriented programming are classes, and these are the objects that basically represent the concepts that we view, and they encapsulate both data and operation, and it sort of become entangled the deeper we go through inheritance or larger the code base. Even if the code base becomes broader rather than deeper, still the entangling of data and operation are still there. And all this causes an obfuscation in how the data and how all these instructions, how they are accessed in real time, rather. We will know how they are laid out in memory if we manually check, if we manually make sure how we line up what data we put one after the other in float after int, stuff like that, right? But how they are accessed in real time, how the data goes to the CPU, all these are obfuscated from us. And this causes a thing called cache misses. And cache miss is core to our problem here, the thing we are trying to solve. So the solution comes in the form of data-oriented design. Entity component system is a pattern, a part of data-oriented design. How it is a way we do data-oriented design, basically, right? And also, I need to point this out that this is not a silver bullet to solve all kinds of problems everywhere. Different types of problems will have different types of solutions, such as you will have a very short deadline and you're used to object programming. You will not try to learn some new paradigm and incorporate this, like hammer it down. If you have good enough time and you have gotten used to this, then you can do, but we will see why we will do this. So what does data-oriented design mean? It basically means that data is the core of our programming. So what data-oriented design, rather than what it assumes, what it tries to put down is that data is core to our programming. And it is true that data is core to programming. More important than the operation, the functions that we type, the structures, the data that we represent, the data or classes that we put, they are the ones that are being moved around in hardware more than the code itself. Data is what is being transformed into one form to another. In the end, all the applications that we make are basically chunks of data and it is being transformed from one form, what it was, to another form, right? And the code is just there to transform the data. And data is what the hardware cares about. The hardware does not care about classes and objects. It does not care about virtual functions and templates. Although they have their place, it does not care about that in the hardware level. Close to the metal, it does not care about that. Data is what hardware cares about.
Yes.
And data is what the large majority of our program constitutes. And code is simply there to transform data. So, purpose of code, we have data A, and it will be transformed. Transform is basically just a function, and yeah, so it's easy to reason, right? But we don't reason with object-oriented programming in this sense. When we are doing object-oriented programming, we don't think about, oh, it's just data which we are transforming. We think about problem and the solution in our conceptual sense. But in the end, it's simply data being transformed. So, two things. Hardware reasons with data. Hardware does not care about human abstractions. This is the point that I'm trying to just hammer down here. So, why is all this important? Why am I talking about data a lot and all these transforms a lot and just think bad things about object-oriented programming? I'm not trying to say object-oriented programming is evil. It has its place, it is good, but the problems and the solutions are different, and this is a solution to a different problem. Right? And let's look at the problem and just hammer down, be sure of what the problem is. All right, it's performance. So CPU, clock speed, and memory access speed. These are the two things that have not taken the same route through time. We have the Moore's law where computing speed doubles every year or so. And it has started to plateau out a bit now, but we can still, like, for the sake of an argument here, let's just say that clock speed is rising. Memory access speed, on the other hand, is not rising. And there's no correlation to it, rather. So, memory bandwidth is still slow. And why is it slow? It's because of physical realities. It's something that we cannot do anything about. It's intrinsic to the copper wiring and electrical charges, the basic physical realities in which
it's the hardware, right?
Yes, it is the hardware.
Yeah.
It is the hardware that matters. So, as you can see in this chart, the performance gap for CPU and memory has gone through a lot of, like, a different route, basically. CPU performance has kept rising, whereas the memory performance has not risen at the same rate. And here you must take care to look at this memory as memory performance speed rather than memory size, because we cannot correlate performance with size. It is basically CPU speed correlated with how fast the memory can be accessed and how fast you can get the data, those kind of speeds, generally put in generic terms. So there's a large performance gap here. And why hasn't it grown as such? So in order to do that, we need to dive a bit deeper into the hardware. So here you can see a picture of a motherboard, right? It's simple, everyone recognizes the CPU and everyone recognizes the RAM. And there's a ruler here to show the distance between the CPU and the RAM, right? And as you can see, the distance, the straight distance, a straight line, a beeline distance between the CPU and the RAM turns out to be around 9 centimeters. Now, why does this matter? Right? Let us suppose that the CPU clock speed is around 3.3 gigahertz. An average normal, pretty fast clock speed CPU. And for the sake of our argument, let us give our memory as much as an advantage it can possibly have. So let's say data travels at the speed of light. Right? So with these parameters, we can say that the distance traveled by data in one clock speed
amounts to the speed of light divided by 3.3 gigahertz, basically the data travel speed divided by the CPU clock speed. And what this happens to amount to is around 9 centimeters. So what this means is that in one clock cycle, when a CPU can execute one instruction in one clock cycle, it takes data around, the data can travel around 9 centimeters. So in one clock cycle, a 3.3 gigahertz CPU's one clock cycle, light will travel 9 centimeters. Just 9 centimeters. Now, we have to consider that first, the data request needs to travel from the CPU to the memory. The memory needs to do its own processing stuff to find the data within it. And then it needs to return that back. And then we also need to take care of that the routing of the wiring does not go in a straight line. It goes to a different route. And memory requests and memory data, the data packets, they are returned and the requests are sent in a thing we call bus. And the bus is basically a bunch of copper wiring. That's all it is. And the charges are not even light packets. It's electrical charges. 0 for 0 and 3.3 volts for 1. And you can imagine that it's not just 9 centimeters that our electrical charges has to travel, and it's not even light, right? And for that reason, we have different things that hardware designers have given us, have come to give us programmers a bit of leeway into solving this problem, because data is traveling at a very slow speed, as we just saw, right? So if the CPU needs a data and the CPU can't, well, basically there's an instruction in the CPU and the instruction needs a data, and the data takes a long time to come, then freezes. Basically all the freezes that almost all the freezes, most of the freezes that you get in applications are because the CPU is waiting for the required data to come in. And that is an inherent problem that programmers have to solve right now. And for that, the hardware designers have helped us by providing us with a few things. And this is important for all programmers to know in this time. We have caches, not just memory, not just dedicated RAM, not just main RAM, we have caches. And we have different types of caches, different levels of caches, a hierarchy of caches, if you will. A CPU within itself has a thing called registers, in which numbers, basically like small data reside, on which the access to which is basically free. As soon as basically that's where we want our data to be when the instruction is trying to execute, right? And on top of that, we have a bunch of caches called L1 cache and the L2 cache, as you can see in this picture. And L basically just refers to level of cache. So level 1 cache and level 2 cache register. Sorry, not register, caches. Level 1 cache and level 2 caches. And the higher you go in the level, the larger the size of the caches, but at the same time, the slower they are, because the further they are distant. Distanced from the CPU. Right? We want our data to be as close to the CPU, as close to the core as we can, as you can put it. So L1 cache is it's smallest, but also it's the fastest. So it takes about 3 cycles for data to get to the CPU. L2 cache, it takes around 20 cycles for the data to reach the CPU. And from main RAM, we have around more than 200 cycles, as you can see in this picture over here. Where the caches are located, where they are present, you get the idea from here. Like we have different cores in CPU, right? This is like core 2, let's say, for the sake of our argument. And L1 cache, they are local to the cores, but they are also closest. They are inside the cores, basically. And L2 caches, they are global sort of caches, and they are the most distant caches from the core, but at the same time, main RAM is outside the CPU and it's distant. It is at a certain distance. And that is why it's the slowest. This is a picture of a die, a CPU die, a magnification of a CPU die. And you can see there are 4 cores. And if you can see my mouse, you can see the small thing here, the small circle here. This is the L1 cache. It is closest to the core, but also the smallest. This is the L2 cache. It is larger than L1, but it is a bit further than L1. And there is also level L3 cache. So in this CPU design, there is 3 levels of caches, and L3 cache here is the global cache, which is furthest from all the cores, but also it is a global one. And the memory controller is the one that checks when an instruction comes in. The memory controller checks if the data required by that instruction is within the cache, L1 cache. If not, then it will check in L2 cache if the data is there. If not, it will check in the L3 cache if the data is there. If not, that is bad news, because the memory controller has to now recall the data all the way from the RAM back to one of the caches and again percolate it higher to the core that requires that data. And it takes time. How long does it take? Exactly how long does it take? Right? That is the question. So to give you an idea of how long it takes, to the left we have, it's a racing basically. The data is trying to go as fast as it can to the CPU. Right? To the right we have the CPU, to the left we have our data. So if our data happens to be, the data that is required by the current instruction happens to be in the L1 cache, this is how long it takes. Pretty instant, like fast, pretty fast, right? 3 clock cycles. If it is in the L2 cache, if it is not in the L1 cache and it happens to be in the L2 cache, this is how long it takes. Right? We're getting slower, but still it's not crippling. Now, if it is neither in L1 nor in L2 cache, and it has to be called from RAM, this is how long it takes. And by the way, this is all 2 scale.
It's exponential.
Yeah, it is. Pretty fast. I mean, opposite of fast. Right? We could make it pretty fast,
Yeah.
but it is pretty opposite of fast. Right, RAM. Very slow. Very slow. And this is the problem we are trying to solve with our entity component system, with our data-oriented design. Now, how is data sent? In what form is data sent? Right. When CPU needs data, it grabs a chunk of memory. It grabs a chunk of memory, that data, from the RAM or the cache or whatever, and it sends it back to the CPU. And usually these chunks of cache are 64 byte to 128 byte. It depends on the implementation of the hardware and stuff. Right?
The architecture
of the CPU and the memory controllers. This chunk of data, this cache line, which is in one of the caches, can be accessed by the CPU much faster because now it is already in the cache instead of having to recall it from the RAM. And you can see a picture of a cache line down there. You can see that there is a byte that we requested from the RAM, and it has returned a cache line of 64 bytes around it. That is around the byte that we requested. And why is this important? Because of 2 terminologies that we need to get familiar with, and they are cache hit and cache miss. So basically, when a CPU, there's an instruction in CPU and it requires a byte of data from the memory, and it is not in one of the caches, what the memory controller does is it requests that byte of data from the RAM. And the RAM, the computer, instead of sending just that 1 byte of data, instead of sending just that 1 byte of data, it sends 64 byte to 128 byte. It depends on the architecture. Let's say it sends 64 byte of data. Instead of just one byte. It sends the 64 byte of data that is around that byte of data in a thing called cache line. The 64 byte of data is called a cache line. It sends that to the CPU, and it goes from L3 to L2 to L1 to the registers, right? And why does a computer do this? It does this because it's a heuristic that that the CPU sort of assumes that the next instruction will most likely require the byte that is around the most recently requested byte. It is an assumption that the CPU makes in order to optimize, in order to make our processing faster, so that we have to go to the RAM as less as we possibly can. Right? That is the reason that the CPU assumes that the data that we requested, the data around the byte that we requested, are the ones that are going to be the ones that we might need in the next instruction. It is an assumption that it makes. And if in the next instruction it does so happen that the data is next to the byte that we requested, then it is already in the cache line that had been sent, right, for that previous byte. And if that is so, then we call it a cache hit. We have hit the cache. It is there. The data is already there in one of our caches, and access to that cache is almost instant. However, in case that it happens that the byte is not there, the next byte that we need is somewhere way off in the RAM, again, somewhere that we have not taken care of packing properly, then it is called a cache miss. In video games, it's thrashing the cache, a bit of a more fun way of saying it. A fun way of saying a very unfun thing. A cache miss.
Cache miss.
Yeah, not fun. So data locality is important. That is why. That is why we need to make our data local to where they are, local to how it is called. Now, in object-oriented programming, how we normally program, let's say to the left, we have an organism class. To the right, we have an animal class.
Animal.
Yeah, which is just inheriting from organism. And they have the data and their own operations. And it is a basic inheritance paradigm we are used to. And now the animal can be inherited by other things like birds or mammals. And mammal can be inherited by a cat or a dog, or humans. So, how it is laid out in memory. So, let's say bird has inherited animal, and there is a hierarchy of so organism inherits from genetic entity, animal inherits from organism, which is in turn inherited by our bird class. So there are levels of hierarchy happening here in our inheritance, in our class. And when you just look at a bird class and you have just inherited from an animal class, right? And you are just looking at the bird class, you would not think that there are all these other data above it. To the right, the data has been unpacked by providing a certain option to Visual Studio. And the size of bird happens to be 56. 56 bytes. And here, alignment member, we have the alignment member you see are basically padding that the compiler automatically pushes in order to make the structure, in order to make this object memory aligned. Basically, in order to access this memory faster, it's best to align the memory in multiples of 4 bytes, and that is what this padding are doing. But regardless, this is all the constituent data that we have right now. Now, if we need to do an operation on this, first of all, we wouldn't even know all this there by just looking at the bird class. We would need to manually go out or do this esoteric options, provide esoteric options to Visual Studio to get how the data is aligned, how the data is basically packed. And if we have to do an operation on this data, for example, let's say we just need to move the bird, right? If we want to move the bird, then we are just taking the position, which is the vector 3, as you can see here, and we will be adding delta time, we will be adding a velocity to it and returning that position back. So basically all we are requiring from bird class in order to move the bird is the position. But we have all this data here. And why does that matter? Because when we are doing this for multiple objects, the cache line, you can see the cache line on top. They are like cut in chunks of 8 bytes, and it's a 64 byte cache line. And for every bird that we do this move operation on, we are not just bringing in the position, we are actually bringing in all this data, all this data that we do not need for moving the bird, and we are packing it in the cache line. And you can see how much space are being wasted. How many, like the space, almost 80% of space is being wasted for the bird for doing this move operation. And you can guarantee that there are going to be cache misses involved in this method. Now, we can conclude that object-oriented programming is not data cache friendly. It is not instruction cache friendly. Basically, it is not cache friendly. And the complexity rises as data and code are entangled together. So we have all these inheritances and virtual functions. After a deep enough thing, we need to map it down in our paper in order to get a good idea about it. And it gets complex the deeper it goes. So we need to start thinking beyond just object-oriented paradigm. We have to think beyond all these things: encapsulation, polymorphism, interfaces, classes, inheritance, all these things that we're used to. And classes and inheritance are basically the ones which are the hardest for us to move beyond, but are also the most important ones, the first ones that we need to stop thinking in terms of. Because classes are basically data and behavior, we're entangling them together. And inheritance, after deep enough, you can see we start to lose our sense, our reasoning of the data that are packed in the classes. What is this yellow? Wait. Sorry about a bit of a hiccup here. Well, anyways, we have a yellow line here, so we'll just try not to look at the yellow line. I don't know how it's there. So, entity component system, right? What is entity component system? So ECS is basically comprised of three important things: entities, components, and systems. Right? And what is now? Okay, so entities are basically they're identifiers. They are numbers that give us. They're basically just identifiers that are combining all the components together. There are certain components that we have that represent a certain physical reality, and these data packets are combined together to form entities, right? So for example, like I might be an entity comprised of a shirt component, an eye component, a nose component, sort of, to give it a more conceptual view. But then again, we are thinking now in terms of hardware, so we have to do away with conceptual abstractions. And systems are basically just functions. They are functions that work on data. They are functions that work on the components or a set of components. So in a visual sense, we have our component A to our right, and we have our component A to our, we have a component A to our left and a component A to our right, and we have a system in the middle, and we have a bunch of component A's for entity 1, 2, 3, 4, or whatever. And the system carries out its operation on all these components, in all these data for different entities, and transforms it according to what is being programmed in the code to a different data, a different form of that component And components are nothing but structs, basically. As you can see, it's a struct. For example, I'm just giving an example of a struct with like 256 bytes of data, right? And it can be any kind of struct. So for example, you can say that a component A comprises of vector 3 position, a vector 3 rotation, and a vector 3 scale, in which case it could be a component transformation, right? It could be a component called component transformation. So it can signify its position, rotation, and scale. And you can have a system to change the position, change the rotation, or scale according to how you would need. And how we would do that, we will see in a while. So entities are basically, you can visualize entities as like a ring in a key ring, where the keys are the components and entities are nothing but the key ring which holds the keys together. So it can be different combination of keys for every key ring, right? So entity 1 is a combination of component A, B, C, and D. 2 has just component A. Entity 3 has components A, B, and C. Entity 4 has again A, B, C, and D. So you can see the pattern. You can see how entities and components are related, interrelated, right? And components are basically just our idea of what data are being are we transforming. So entities, they are related to a collection of components. They don't themselves contain components. That you have to understand, that entities are not classes. Entities are not classes, and components are not like just position or rotation or scale or certain data structs within those classes. Otherwise, that would be just going back to the object-oriented paradigm. Entity is just related to the component, and how we can relate them is a implementation semantic, and there are different types of different ways to do this. We will see that later, but they are not containing the components. They are referring components, and these are simply global universal IDs or numbers that identify themselves, are identifiers to identify themselves as something unique among other identities, other entities. Sorry. So an entity is simply a number or an identifier which identifies itself as a unique entity among other entities in the world. And sometimes they contain components information, and it is called a hybrid system, a hybrid of data-oriented and object-oriented, mixing them together, but it is dependent on implementation. Right. But in most cases where performance is too critical, they are kept as simple numbers. Now, components. Components are data structures that represent a certain property or a data. As we just saw, it's a simple struct, right? And these simple structs are sometimes called plain old data, where we just have a struct of native data types, of primitives, a struct of primitives, and they are called plain old data. And they do not contain any operational information, no functions inside those structs or classes. It's not even classes, basically, because if you use class, they are private by default. So why would you use it, right? Just use structs because they are public by default. Yeah, they do not contain any functions at all, components. For example, you could say a rigid body component. A rigid body component would have information related to the physics of for collision. For example, the dimensions of the collision box, the position of the collision box, the radius of a capsule, stuff like that, which is related to our physics system. Our AI component would have, again, like information related to like the AI programming system we have. Input component, player component, position component, velocity component. It depends on what you're trying to solve and how you would do it. You're just representing data that you will be sending from RAM to the CPU. Now, systems are systems finally are just operations, just functions, plain old functions that are working on a certain component, one component or a set of components. We can say this system carry this function out on all the entities that have component A, C, and D. Only on those entities which have component A, C, and D, get all these components and carry out this operation on all of them. That's all that systems do. So they are basically functions, as we just established. So we can have a pathfinding system which could ask for all the entities, which would query for, okay, return me all the entities which have component AI component and which would have enemy component, and now do the pathfinding system on that. So in that way, like it would, or like a collision component, right? So in that way, it could ask for these entities, and it would get them in one cache line, in a bunch of cache lines, one after the other, and it would do all the calculation on that, and we would ensure that cache is always hit. Movement system, similarly for player and input component. Sorry, there's a typo here. This is supposed to be input component. So ECS is so in a larger sense, in a global sense. Now that we know what entities, components, and systems are, so ECS in a larger sense, it is implemented as a database system. It takes a form of a database, a relational database. And you would have an idea that, oh, SQL and all these are very bad at runtime, very slow. Relational database is sort of like a modern leap in performance that we have achieved in database systems, and it can be implemented specifically to solve performance critical problems in runtime applications, like even games. And entities acts, so you can think of entities as keys to the component instantiated within the memory, and the database system will relate these entities to their respective constituent components, right? And system would then, for every loop, every game loop, the system would then query for all the entities for a set of component that it needs to carry out its function on and its operation on, and the database system will return these component data in a perfectly managed cache line and in a perfectly managed chunk consisting of one cache line after the other of only the required data, no superfluous unnecessary data, only the required components packed in together, sent to the CPU, and the system will carry all the operations out as fast as possible. And the backend here will return a packed stream of components in chunks, 64 bytes each cache line, and the chunks could be 64 kilobytes. I think Unity does 64 kilobytes chunks to send the data back, and system executes the code on that stream. And the execution can happen only as fast as the data can be found in the cache, right? So for a basic example of how we would just call these things, a naive implementation, a sort of hybrid. I should have called it hybrid, but I call it naive because it's very easily implementable. You just need pointers to the components, right? So how we would do this, let's say our components are just a bunch of pointers to the component data that have been instantiated within the memory. And each entity will have these components. And to get a certain component for a certain entity, we would just provide the entity number as an index to these, right? And that's how we would access the components. And in the loop, we would just process all the AI. We would do the AI system on all the AI components for all the entities. Then we would do the physics collision detection systems in collision resolution systems in all the physics components. Then we would do this. We would do all the drawing for all the entities that have render components. And as you can see here, the data and the object loop, the function is intertwined. You have operation, you have implementational information within the component here, and hence the naive hence a hybrid approach to solving this. And by doing this, you can ensure that you are operating the same update information on different chunks of data. So the data is different, but instruction is same, right? So the instruction will be the same in instruction cache and the cache in CPU, but the data will be constantly changing. And if you have all the AI components cached in cache lines one after the other, it does not need to go to the RAM. And no hiccups, no stuttering, no freezes, fast execution speed. The cache lines will be written as such. Example 2, here I'm using a library, you can find it on GitHub, called Flex. It is a C++ library. It's even compatible with C89 C89 implementation, so specification. So here we have our components, struct position and a struct velocity. Plain old data having primitives float xy, to signify direction and position point. So we instantiate our world of ECS with world ECS, and we create an entity by calling as such. We create an entity.entity. We give it a name, and you have to take care that here we have given a name, a string. It depends on implementation, but generally entities would not have any string. Sometimes in some libraries you would not find strings or such, and in such cases how you would identify, how you would call. Here it is, we have named it an entity with a string because we can now query for a specific entity where we can say like, okay, return me this entity instead of this set of components. And if you would want to do it in a pure ECS sense, without any string like that to identify an entity, which is just a number that the compiler would like just would automatically, rather than compiler, the runtime would automatically give a number to the entity. You could not specify a certain entity. In such cases, you would create an empty struct. You would create an empty struct, a struct my player, right? You would create an empty struct, and now it won't contain any, it won't take up any space in memory. However, you can like query for that struct component, right? Now you can say, give me all the entities that have component position, velocity, and component player one. And player one would have nothing. It would just, it would be an identifier basically, and it would return player one. It's a very different way of thinking about programming. It's not object oriented at all, and it will take time to get used to it, but it's a very important for performance reasons. So after having, so we then set the component. We say that entity, my entity has component position and velocity, and we just give it a constructor. We instantiate it with default data, and then we create a system. And we say, let's say we have a bunch of entities which have been instantiated like that. And then how we would call the system is like, we would say for every, you can see this is a templated system, a templated function. We are saying, okay, for every, we do the system on every entity which has position and velocity. And we are putting a const in front of velocity in order to signify that, okay, velocity should not be modified. Only position can be modified in this. And for each, we are doing a lambda function where for every entity, we are just incrementing the position, and it is similar to the, so if we do this, like it is a very similar thing which we did with the bird, as you might remember from before, the object-oriented way. For the bird, we did a similar thing, but in an object-oriented way, and this is the same thing, equivalent thing, but in entity with the entity component system. And with this, like, yeah, same thing, right, with the bird, and we had these kind of cache lines. And now with this one, we can ensure that our cache line is filled with only position. Okay, we just need the position from the bird. We don't need anything else. And now it will be packed like this, and we can have almost 50 times, maybe more, 50 times more speed than with, compared to this. Yeah, so we can have, well, 50 times more birds, or sometimes 100 times more birds. More birds, more the birds, more the fun. So now, after looking at what ECS is, let's see what ECS is not. What not to be confused with. We should not be confused with the component-based systems that you could see in the programming world and these different game engines that we have, commercial game engines like Unity, Unreal Engine. They all say that they have component systems, right? And they have component systems. It is true, but it is not entity component system. They basically have components which are attached to a thing they call entity, or sometimes they call game object, and they do operations on that. But it is highly object oriented.
Yeah,
No,
object
no,
oriented.
Yeah. CryEngines is the one which is closest to ECS, but even that, please do research on CryEngine. But on Unity and Unreal Engine, yeah, it is not. No, it is not.
The default is no.
No, default is no. Now, the interesting thing is that Unity has realized that this is not a performant thing, and now they are slowly moving on to a data-oriented stack.
Yeah.
So they have both implementations in place, and it is nice because now we can compare both of them for the same software, right? We can compare the performance. We can see like how it works. For mono behavior, which is their object-oriented way, the way they would do it is we have a game object, which is their entity, and it is called point light. Yeah, you can see here the entity is named point light.
Point light component.
No. Point light
component
is
light.
Yeah, with the component light and the component transform. But there is both implementation and both data and information within these components, and they will be executed cache unfriendly. Yeah. Similarly, we have
Many
cube
cache
here.
miss.
Many cache miss. Similarly, we have cube here, a cube game object, and it has component transform, component cube, component mesh render, component box collider, but not ECS. Please take care of that. And this is how they do it. Mono behavior. I just put it to give a better view. But the ECS implementation is very different, right? As you can see here, to your left, they have instantiated position and velocity. A very similar example as we saw before, but in Unity terms. Position and velocity, they are just inheriting from something called I-component data, and it's fine. We see here a bit of object-oriented paradigm, but it's fine because the implementation detail is C++. They have implemented the backend database system with C++. And this is their scripting system, where we are using just one level of object-oriented paradigm, where this is the extent of object-orientedness that we would have in Unity, because it is C#. C# is a heavy object-oriented language, and Unity uses C# for scripting. However, the backend is C++. And yeah, they have inherited from I-component data just to signify that this is a component. It does not add any component, any data information in it. No extra information. The primitives, the value that you see there, that the components, the member components that you see there, the member attributes that are there, are the data, are only the data that are there. I-component data is just there to signal the backend that, oh, this is a component. And then we have another class called ECS system, which is taken from system-based, similar to the component data. It is just there to signal the backend that, okay, this is a system. And inside we have on update. And on it, what we are doing is like, okay, for each entity with name update displacement. No, the name is basically the name of the system, just for debug purposes. And it's not naming, it's not giving any name, any string, attaching any string to the entities or anything. It's just there so that when we're profiling it in our profiler, memory profiler, this name will be shown so that we can see which system is currently being the update displacement system is just going to take position and velocity data and will be adding it as such, similar to the bird thing. And with that, only the position and the velocity data will be packed, and it will be performant. And how the backend is working here, the C++ backend, how it is working here is there are two terminologies that we have to be familiar with called archetype and chunk. When you are implementing your own ECS backend, you would have an archetype, which is basically a predefined combination of components. It is not an entity. It is just defining a combination of components. And when you would want to instantiate an entity, every time specifying the component data, rather than doing that, we can just say, okay, instantiate an entity of this archetype. And this archetype will possibly have like just position or float, right? So this archetype will have just position or float. So yeah, these are the two ways we are creating the entity. We are just saying create entity. So the first one, create entity, and we are giving it a list of component types. Specifically, we are explicitly giving them the different component types, or we have already specified an archetype with those component types. Then we can just say, okay, this archetype, create that entity. And when we create that and a system requests these type of entities of this archetype, then the backend will pack all the entities with all those components. Suppose this is like position and velocity, as we saw in this example. It will pack all the entities in chunks and return that. So in one chunk, we have one entity. No, in one chunk, we have as much entity as it can pack, 64 kilobyte. As I said before, it's around 60 kilobyte a chunk, so it can pack in around 1,000 entities, I guess. So if each is 64 bytes, then it can pack 1,000 entities in one chunk. And if it cannot, then it will send another chunk with the other 1,000 entities, so 2,000, 3,000, 4,000, stuff like that. So this is how the backend you would formulate, and the semantic implementation is beyond this talk, because there are a lot of things about database and how you would do that. You can even do it without implementing database. You can find it in the internet easily, right, how you would implement this. Just type entity component system and you will find a data-oriented implementation, how you would implement the backend. Or if you don't want to implement the backend, just want to use it, and then you just want to use it with this paradigm in mind, then you can download a bunch of libraries that are already available. And they are implemented with C. Because this paradigm was way back. It was already started with C. We just forgot about it because this object-oriented culture took over, and we're used to this now because it's used in all the enterprises and all the companies. It just happened to be. Object-oriented wasn't used because it was performant. It just was easier to write. And this, I would argue, is easier to code a large code base because you can see exactly what data are being transformed by a certain function. In object-oriented programming, you would have a function which is modifying a bunch of data, not just the ones within that class, but other classes as well. And it would take a long time to figure out exactly what is being transformed. With the system, entity component system, you have one function which specifically specifies exactly what component it is transforming, and it is easy to track these down, a lot easier. And with this, I would, like all this heavy theoretical talk, I would say like these references were really helpful for me while I was doing research for this. Data-oriented design by Richard Fady, and it has a bit of implementation detail on the database system. It's a book, but it is very dense and very difficult to go like all in without a general conceptual view. So do your own research, people. You can look into Unity's ECS architecture that they are implementing, their manual, and you can just use their implementation to get a better feel of how you would program in this environment. Game engine architecture by Jason Gregory is nice to get a view of basically the hardware and a general overview. It's not just ECS, it'll give you a general overview of these cache things I've talked about. And game programming pattern has one pattern called, I think it's called optimization through data locality or something. And that talks a bit about these cache lines and how you would that in a hybrid sense, though. It's not pure ECS. And with that, I would like to finish a theoretical part. I'm sorry if it dragged on a bit too much, but it was important for you to understand the next one, which is going to be Masfu's practical one, which is going to be more fun, I'm sure, than my.
I don't know about it. Okay, thank you, Pratius.
Thank you very much.
Terima kasih.
Yeah, thank you very much for sitting through this. I'm sorry if I want too much, but I'm also hopeful that it was very interesting. Thank you very much. Thank you.
Ya, oke, terima kasih.
Terima kasih. Matur nuwun.
Oh ya, buat teman-teman yang pengen nanya, jangan lupa nulis di Slido ya. Ini baru ada 2 penanya, nanti akan dijawab habis sesi selanjutnya ya, mengenai DOTS dan ECS. Tapi lebih ke nanti saya akan tunjukkan di implementasi di Unity dan di C atau C++ menggunakan Flex. Jadi mungkin lebih ke preview, bukan demo step by step, itu pasti lama banget. Jadi nanti akan preview aja. Oke. Yeah, maybe you could stop the sharing. And now,
Stop.
okay.
Should I
Stop share. This is
where's the stop share?
this stop share.
The
red.
All right.
Button.
All right. Sorry.
Okay. There's no option to share the entire screen. Okay, maybe I will try this. Oke, untuk saya mungkin akan menggunakan bahasa Indonesia. Oke, jadi judulnya DOTS dan ECS in Practice. Jadi tadi udah dijelaskan sama Pratius mengenai teorinya dan kaitannya dengan hardware. Memang untuk performa akan pengaruh banget, apalagi untuk aplikasi yang menggunakan banyak memori ya dan banyak objek, kayak di game contohnya. Nah, pertama kan saya bahas mengenai ECS di Unity, Entity Component System. Kalau bagi yang udah pernah ikutin tutorialnya untuk ECS, itu ECS ini dengan menggunakan ECS coding style, kita bisa improve performance, readability, sama reusability. Nah, dan juga di Unity itu disupport menggunakan burst compiler sama C# job system untuk multithreading ya. Lalu nanti konsepnya adalah kita akan mengkonversi object oriented programming ke data oriented design. Nah, kalau untuk Unity mungkin saya akan pakai mikrofonnya Pratius ya. Jadi untuk soundnya stay di Pratius saja nggak apa-apa. Karena di tempat saya agak bermasalah untuk masalah mikrofonnya. Stay mute aja ya. Oke, untuk setup-nya lewat Unity Editor itu di build setting, project setting, other setting, kita perlu setup dulu ke API ya. API compatibility-nya ke 4X, lalu Unity-nya perlu di restart. Setelah itu kita perlu modifikasi package manager. Jadi untuk mengimplementasikan entity component system, kita perlu menggunakan package manager untuk ngedownload si package buat entities-nya ini. Jadi nanti terpisah dari default-nya. Nah, ini ya, entity component system. Ini ada beberapa referensi ya. Lalu dari package ya, package-nya di folder package itu ada manifest.json. Perlu kita tambahkan dependensi incremental compiler dan entities. Jadi dua package ini dibutuhkan juga. Lalu nanti ketika udah kita modifikasi manifest.json-nya, kita bisa restart atau relaunch Unity-nya, lalu nanti kita bisa lihat di package manager di Unity, nanti bisa lihat semua package yang ada di project kita, dan ada beberapa keterangannya ya. Misalnya ada error, ini ada keterangan loading package-nya error. Gitu. Biasanya error tuh karena network sih. Kalau lancar aja nggak perlu khawatir. Gitu. Nah ini contohnya entities di preview 8 versinya. Jadi kalau untuk entities ini sampai sekarang masih di preview ya. Lalu ini seperti ini ya bentuknya entity component system. Ini defaultnya biasanya kalau di Unity itu menggunakan game object ya. Di dalam game ini menggunakan beberapa mono behavior namanya gitu. Atau kita biasa sebut game komponen ya. Jadi game object di dalamnya memiliki banyak game komponen atau mono behavior. Kayak tadi yang seperti ditunjukkan Pratius itu contohnya lighting, lalu rigid body, transform, dan lain-lain. Nah ini contohnya hero ya, renderer, rigid body, movement. Lalu kita akan mengubah defaultnya menjadi entities, components, dan system. Nah entities itu simpelnya ya sama seperti game object sih sebenarnya, components, container. Tapi ini lebih ringan daripada game object. Dan components itu sendiri, itu nanti isinya cuma data aja. Tadi udah dijelaskan sama Pratius juga, bahwa components itu cuma plain data. Lalu logiknya itu akan di-handle oleh yang namanya systems. Di sini kita bisa bilang bahwa sistem itu adalah kontainernya behavior. Itu logiknya ada di situ. Gitu ya. Nah, dulu jadi yang sekarang udah deprecated ya hybrid ini ya. Dulu ada hybrid sama pure. Nah, sekarang yang hybrid ini udah deprecated. Ini contohnya seperti ini, standarnya ada mono behavior, itu ada data dan behavior ya. Bisa dilihat di sini. Tapi kalau kita menggunakan di sini keterangannya hybrid ECS, kita akan pisahkan behavior-nya sendiri. Jadi nanti mono behavior akan berisi tentang data doang. Nggak ada behavior di situ. Nah, ini code example-nya tadi sudah diperlihatkan sama Pratius. Ini yang udah deprecated ya. Seperti ini. Waktu masih ada hybrid, bentuknya kayak gini. Ya, di sini kita bisa bikin script yang namanya rotator ya. Rotator itu contohnya misalnya untuk ngerotate game object. Itu dia punya data speed. Lalu kita buat satu kelas rotator system. Jadi di sini akan berisi behavior-nya. Nah, dia merupakan anak dari komponen sistem ya. Di sini komponennya rotator sama transform. Lalu behavior-nya kita kasih di fungsi onUpdate, kita akan override di sini untuk setiap entity yang mempunyai komponen lakukan transform rotate. Seperti itu, sesimpel itu aja. Jadi setiap game object yang memiliki komponen atau entities ya, kita sebut entities yang memiliki komponen rotator, dia akan di-rotate seperti itu. Nah, ini referensi dari Unity Hybrid ECS udah deprecated. Misalnya kalian penasaran bisa diklik aja di link ini, Learn Unity Tutorial Entity Component System, tapi itu udah deprecated karena udah digantikan sama yang namanya dots. Nah, kita beralih ke dots di Unity ya. Nah, konsepnya itu menggunakan pure ECS ya. Kalau pure ECS itu nanti kita anggap aja udah nggak menggunakan game object sama sekali. Tapi kita menggunakan entities. Nggak ada lagi yang namanya mono behavior. Data akan dihandle sama components, logic akan dihandle sama system. Dan juga nanti akan ketambahan C# job system ya, menggunakan burst compiler dan multi threading. Nah, DOTS itu sendiri namanya data oriented technology stack. Nah, seperti ini ya. Elemennya adalah jadi ECS itu merupakan elemen dari DOTS atau Data Oriented Technology Stack. Jadi yang pertama adalah ECS itu sendiri, yang kedua C# Job System. Nah, yang entity tadi ya, Entity Component System itu ada di package Entities Package ya. Jadi di manifest.json ditambahkan package entities. Untuk C# job systemnya itu package-nya namanya job, lalu untuk burst compiler itu ada burst package, lalu yang terakhir native container which are ECS data structure, itu merupakan data strukturnya yang digunakan untuk mengontrol memorinya. Ini lebih ke native ya, jadi dia yang nge-handle memorinya, nanti API dari si entities package ini. Nah, kita akan lihat di project docs ya. Sekarang saya pindah ke sebentar. Share.
I think the first one is it?
Whiteboard.
This one.
This one. This is Unity Hub. It will switch. Okay, maybe ya. Kelihatan ya dots compile.
You can switch it.
Ya. Masih loading ya, jadi ditunggu sebentar. Oke. Alright. Nah, ini contohnya. Untuk link GitHub-nya udah saya sertakan di referensi ya. Ada slide untuk referensi. Misalnya kalian tertarik untuk lihat apa yang ada di dalam project ini, bisa kalian clone ya lewat GitHub. Gitu, lalu kita buka scenes-nya. Di sini ada scenes.compare, udah kebuka ya di sini. Lalu di sini dia menyediakan beberapa approach di game manager. Nah, ada menggunakan klasik. Klasik itu yang default ya di sini. Bisa dilihat di sebelah kanan di inspektornya. Ini aku seleksi game manager. Lalu di inspector dia menyediakan klasik, ECS pure sama ECS conversion. Kita tes di klasik dulu ya. Jadi nanti ceritanya project ini adalah dia akan generate sejumlah cubes ya. Di sini tiap kali spawn ada 5.000 cubes. 5.000 objek digambar bersamaan. Nanti kita akan bandingkan menggunakan ECS dan nggak menggunakan ECS. Kita akan coba yang nggak pakai ECS dulu. Dan di sini job sama burst-nya aku turn off. Jadi benar-benar pakai approach-nya Unity ketika gambar 5.000 cubes. Nah, ini kita lihat FPS-nya. Maybe we could. something is wrong. Maybe it's because
Oh, yeah.
yeah, this is it.
Yeah. German.
Okay.
Just maximize it. It's fine.
Maybe we should stop this first because only white on the screen.
Yeah, maybe because of the share screens.
Maybe because of the
Can't
shares.
see full. Oh.
Oh,
Yeah, you can't see in the.
Wait, sebentar.
Unity just crashed.
Iya.
Alright, bear with us. We're restarting Unity again.
Mungkin karena nggak pakai ECS ya, jadi nge-crash. Oke, aku akan ulang. Oh, wrong project. Tunggu sebentar ya. Ya, this is it. Ya, mohon maaf, tadi terjadi kesalahan teknis. Jadi Unity-nya nge-crash.
Blame Unity.
Blame Unity. Oke, tadi kita pakai klasik, job sama burst-nya turn off ya di sini. Kita
Where's
coba
the start with full screen thing? It's the new UI.
UI.
Otherwise, there used to be like with full screen on the side. Double click the game.
Nothing.
Everything that used to work, they've changed. Oh, there it is. Maximize on play.
Maximize.
Yeah, fine. Okay, just stop it and do it again.
Alright. Where is it?
Yeah.
Alright. Nice.
Basic
Okay.
stuff. We don't use Unity. We don't use Unity much, as you have seen.
Use C++.
Yeah.
Oke, nanti saya akan tunjukkan yang library-nya yang dipakai C++ untuk ECS. Bisa dilihat di sini FPS-nya masih di kisaran 100-an ya. Kita akan generate 5.000 cubes space. Ya, iya. Lihat FPS-nya ngedrop ke 30. Ini cuman 5.000. Oke, kita tambah jadi 10.000. FPS-nya sekarang ada di 18. Kita tambah lagi 15.000. Tambah turun. FPS-nya sekarang 9, 10, 8. Jadi bisa dilihat di sini makin banyak box-nya, FPS-nya lemot ya.
The more we do that, the closer we are going to another crash.
Iya. Closer to the crash. Oke. Ya, bisa dilihat ya, FPS-nya tadi di angka 30.000. Ini tanpa ECS ya, teman-teman ya. Nah, sekarang kita coba menggunakan ECS. ECS yang mungkin tanpa job sama burst ya. Ini ECS pure sama conversion itu hampir sama. Jadi cuman beda dikit di code-nya, nggak banyak-banyak amat. Jadi dan hasilnya juga mirip-mirip. Jadi yang mana aja boleh. Kita coba yang conversion. tanpa job sama burst.
So conversion is a hybrid, right?
No,
No?
it's not using the hybrid.
Okay.
Yeah, it's the improvement of ECS pure. Oh, you do. Okay, let's play. Okay, let's wait.
Alright.
Nah,
Alright.
sekarang kita menggunakan ECS conversion tanpa burst compiler sama jobs. Coba kita lihat tadi di angka 30.000 ya. Ini di angka 5.000 dia ngedrop ke 60 fps. Tadi yang tanpa ECS itu di angka 30-an. Kalau masih ingat. Nah, di 10.000 dia ngedrop ke 40. Oke, masih bisa diterima. 15.000 di 30. 20.000 di angka 20. Oh, masih mencapai 30 ya di sini ya. Ada 27. Ya rata-rata di 27. Lalu kita coba 25.000. Oke, masih di 20-an. Masih bisa diterima ya. Sekarang 30.000. Itu di FPS-nya 20. Oke, masih playable. Tergantung mesin juga ya. Jadi tergantung laptop saya juga. Oke, bisa dilihat tadi yangnya bisa sampai 8 fps, 9 fps. Ini 35.000 masih di angka 18. Coba kita menggunakan yang job sama burst ya. Nah, ini job sama burst-nya aku hidupin. Kita coba play. Now let's see what's the difference
with the jobs.
Yeah, with the jobs and the burst compiler. Oke, langsung generate. Oke, 5.000 cube masih di 90-an fps. Nice. 90. 10.000 dia masih bisa di angka 70 fps. 15.000 60-an. 20.000 di 50-60. Oke, 25.000 di 50-an. 30.000 masih bisa mencapai 60 fps. Ini jika kita mengimplementasikan ECS dan menggunakan C# LTS.
They're asking whether to use LTS or the latest. You can use any, like use the latest if you want to experiment because it's going to be unstable as well. But the package is I think compatible with LTS as well.
Yes.
Yeah. And by the way, the video stream it might be a bit choppy, but FPS for us is actually 63. It's like it's just like a number 64 and then it's choppy. It is actually very smooth for us. It's choppy for us.
It's only because of the shares.
Yeah. Imagine it is very smooth. It is 60 FPS. Yeah.
Look at the FPS.
Yeah, look at the FPS basically.
60 FPS for 30,000 of cube. Okay. Oh, we could add as much as 70,000 of cubes. It's still on 30 FPS. Bisa dilihat di sini ya. 80.000 jumlah cube-nya dan FPS-nya masih di 30. Jadi memang pengaruh banget ya di sini antara menggunakan ECS dan nggak pakai ECS sama sekali. Jadi does GPU play a role here?
Or is it? No, wait. So this is CPU bound. GPU here is just instancing. Like it's the same data that the GPU is instancing. So GPU is not an issue here. CPU issue because there are so many cubes and the data position is having to be updated for all the cubes for 80,000 cubes, right?
Yeah.
And Yeah, the memory of 80,000, the data for the position data for 80,000 cubes, and the render data for 80,000 cubes are having to be back and forth between the CPU and the cache. I mean, the CPU and the memory.
And actually, ECS looks like GPU because GPU already using the data-oriented design.
Yeah, like we're sending in this and index data to buffers, and then we can render as many of that objects in the buffer as we want.
Jadi sebenarnya ECS ini nyontek approach-nya GPU. Jadi approach yang ada di GPU dibawa ke CPU.
You can think of shaders as the systems because they are just carrying out one operation on a bunch of data, the vertices, the indexes, or anything. And that's what we're emulating in CPU. So it's not exactly one-to-one, but you can sort of think to get an idea of conceptually how we use paradigm.
Ya. Oke, perlukah kita lihat code-nya seperti apa untuk ECS-nya? Lihat code-nya. Jadi di sini ada beberapa script. Kita lihat di script-nya. Di sini ada script yang untuk klasik dan ECS. Ini untuk manajernya ya, yang untuk nge-setup tadi pakai ECS atau enggak, lalu pakai job atau enggak, itu dikontrol sama manager yang ada di sini. Ada spawner manager sama game manager. Kita bisa lihat di klasik movement-nya kayak gimana, kita lihat ya. Kita bisa lihat di maybe we will crash here because of the Visual Studio. It's heavy, man.
Oh yeah, Visual Studio is very heavy.
Visual Studio. Okay. No share. Okay. What happened?
Visual Studio.
Yeah.
Oh
No.
oh
Oh, it's not blue screen.
oh yeah. Actually, Visual Studio crashed.
Oh wow.
Oh my goodness.
Heavy processing here. Oke, kita bisa lihat dari inspektornya.
Visual Studio.
Visual Studio crash.
Just use Notepad++.
Oke.
Or Emacs. Emacs is good.
Ya, bisa dilihat di inspektornya. Di sini class movement adalah mono behavior. Ya, seperti kalau kita pakai Unity buat kelas, ya dia merupakan otomatis dia akan dianggap sebagai mono behavior. Lalu di sini dia punya beberapa fungsi yang bisa kita operate. Di sini logiknya. Jadi dia transformnya akan diproses di sini. Ya, seperti biasa, normal, mono behavior. Jadi kita pakai fungsi, kita tuliskan prosesnya di situ. Mono behavior. Dan datanya juga masuk di sini. Tapi kalau kita lihat di ECS ya, di sini ada data sama sistem. Jadi udah dipisahkan untuk data. Nah, kita bisa lihat di sini. Oh no, bro. Double click accidentally.
Okay, let's see. Let's
see.
have faith. Let's all pray for Visual Studio.
Oke, kita bisa lihat di inspector bahwa move forward itu adalah komponen data dan dia cuma berisi speak doang. Dah, itu aja. Jadi komponen di sini memang data. Lalu kita lihat sistem. Oke, bro.
Okay, now we have to wait for Visual Studio to come back to life. Okay.
No chance, bro. Visual Studio. Unity plus Visual Studio.
Double heavy. Unity is nice. It crashes video.
Yeah. There's no. Maybe I should solve.
Why don't you use Mono, sir? Mono. Mono, we don't use Mono because Visual Studio is usually the industry standard. It's easier to program.
Easier.
Yeah, we're used to Visual Studio. You know, it's how do you put it? So there's code highlighting and stuff that we are used to when we're programming, and Visual Studio is nice. The computer in which we are loading this right now is not a powerful one. It is a very not so powerful laptop, and
Yeah.
that is the reason. But when we're using Visual Studio, we usually use it in a computer that is fine, not which has enough RAM and stuff.
Just admit that we all love the smart intelligence.
IntelliSense. Oh yeah. Oh, I forgot to talk about that. IntelliSense.
Disregarding the
Oh, yeah.
intelligence. Case miss.
Yeah.
Case miss.
That is a personal cache miss. Okay. IntelliSense is the it's one of the most nice reasons why we use Visual Studio.
Yeah. Kami akan restart Unity-nya. Heavy, bro. Heavy stuff here.
We're loading back Unity.
Yeah, but where is the swing? Does it come? No? Oh, this is this one. Okay.
Get rid of all the formats, right?
Yeah.
Yeah. Because this is not so powerful.
A lot of
All
case
right.
misses.
All right, yeah. We're back. We're back.
We back.
Back in action.
Okay, the scripts. So tadi data kita udah lihat, lalu kita bisa lihat di sistemnya. Kalau kita lihat di sistemnya ya, di sini ada 3 source code. Jadi yang movement system sama ada movement system jobs, itu untuk jobsnya. Lalu ada movement system jobs burst, itu jobs plus burst compiler, gitu. Ya, jadi isinya cuma logic doang. Di sini nggak ada data ya. Cuman di sini ada logic untuk setiap komponen yang memiliki trans sama move forward, kita lakukan logic ini, gitu. Kita tambahkan forward speed di sini. Bisa dilihat seperti ini ya. Jadi ini menggunakan job component system di fungsi on update. Lalu di sini ada query ya. Kita sebut ini query for each. Jadi yang kita query itu entity dengan komponen apa? Untuk setiap entity dengan komponen. Jadi komponen kan bisa banyak banget. Ada komponen lighting, form, yang ini yang dieditkan kebetulan yang kita ubah kebetulan adalah komponen transform doang. Tapi mungkin itu bisa jadi kalau di game ada physics, ada lighting juga. Jadi itu bisa membantu, istilahnya kalau game yang kompleks kan ada physicsnya, itu akan mempengaruhi FPS dari gamenya ya. Jadi semakin heavy komputasinya, dia performanya akan semakin ngedrop. Makanya di sini ICS akan sangat membantu. Misalnya kita buat game yang punya banyak objek. Ini ada contohnya sih, bisa kita contohin. Mungkin aku akan kasih contoh. Masih punya waktu enggak ya? Masih cukup ya kayaknya.
Ya, 5 menit mungkin.
5 menit. Oke.
What's the previous instance of media is?
.com. Should I close this? Alright. Ini example dari game yang menggunakan ECS. Dia punya 2 ya. Ini ada Swarm demo ECS sama Swarm. Kita coba yang non ECS dulu ya. Oh, ya. Oh, iya. Okay.
No, just this one maximize and this one do it. Alright.
Wah, nggak canggih nih, Mas.
You can move around, I guess.
Move around.
Yeah, I think you can.
Okay, let's try.
All right. So this is with ECS.
Look time here.
So this is ECS.
This is the non-ECS.
Okay, that was
Okay,
non-ECS.
let's try the ECS.
Okay, so that was the non-ECS. Now this is ECS.
This is ECS.
This is entity components.
Is there any difference? But I don't think.
Oh, Unity just again.
Press again. Oke, mungkin cukup itu ya. Kalau mau nyoba, saya udah sediakan linknya untuk bisa di-clone. Yeah.
These are the things we live with if we choose to do live coding sessions.
Yeah.
Live demo sessions.
Many troubleshooting, bro.
Yeah. It's a risk we took.
What is this? Okay.
Crashes everywhere.
Okay, maybe we could move this.
Move this.
Oke, mungkin itu aja ya demo dari kami. Ada satu lagi, Flex. Cuman ini karena untuk Visual Studio ternyata terlalu berat kalau untuk di share screen kan. Jadi mungkin kita bisa akhiri aja. Fin.
Yeah.
Alright.
So basically, wait, it's not showing.
Oke, mungkin kita bisa langsung ke sesi tanya jawab ya.
Ya, kita
Maybe you could open the Slido.
Oh yeah.
Yeah.
Okay. Right. Stop share. Let me stop share for a while, guys. We're using Edge of all things.
Slido.
Slido. Bear with us. We're going to Slido, right?
Yes. The ID is 73971. Seven three nine.
739.
Oh.
Not bad.
Halo Mas
Right.
Wijanarko.
739.
71.
Ya,
Ya, Mas Wijanarko boleh nampilin ini nggak? Nampilin apa namanya slide-nya di screen?
Share.
Ya ini Pratius sudah
Oke.
nampilin ya. Oke.
Alright. Okay.
First question.
First question. I understand that ECS is an architecture that was used mostly on game dev, but do you think data-oriented design paradigm can also be applied? Yes, it definitely can. It's can we? Is it possible? Is there another view for this?
Another for what?
All right. Anyways, so yeah, it can be used for applications besides game dev because. So see, there are two sides of arguments here. When someone says, "Why would I need to do data-oriented design? Why I would need to do entity component system?" The company I work in, the application that I am in right now, does not require like the requirements for us is to have something happen as fast as possible, and if we can use STL and one line of code to add something to a data to transform something, then I would do that. So there's that person, one side of an argument says that, and there's another side. It is that very reason why a person would do that sort of thing, that would like make that application slow. For example, you just saw Visual Studio, how it was destroying us right now. One of the reasons is because they are, I'm pretty sure, I don't know, I don't have access to Microsoft Code or whatever, but if I were to guess, they are heavily object-oriented design,
Yes.
that application, and that is the reason that it is not as performant as it could be. It is not designed for the hardware, rather it is designed the software itself as a platform, so to speak. So I hope that answers your question, that it has its place in other applications, and if you use it in other applications, it will become faster than it already is. Yeah, you can see even Microsoft Word, Microsoft PowerPoint, and stuff like that. It takes time to launch. Yeah, it's used in it is actually still used in other applications besides game development as well. In game development, a lot of AAA companies, the cache hit is bread and butter. If you're working in video games, by the way, you have to know about that. If you are optimizing, if you are aiming for a performant engine, if you're coding for engine, you have to know about that. So I hope that answers your question.
Okay, second.
All right, second one. How to know when we need to stop looking at data? Let's just do that so that we know we are looking at which question.
Yes.
How to know when we need to stop looking at data, or is there a point when we could say that data are not
Take effect
anymore in our system design? Yeah, so data takes effect in everything, all the time in your system design, right? It takes effect every time. But the question is, when would I have to look at every data that I'm that is hitting that I'm transforming? Would I have to look at every data that my application is transforming or changing? If you want to eke out as much performance as possible, yes. But the sad truth is that a lot of applications, a lot of code bases that you will be going in, that you will be modifying, have already chosen a certain paradigm, and more often than not, it is object-oriented design. Right? Even the engines, game engines, are mostly object-oriented design. Choice, and it is not just choice. It is something that you do, that you would convert if you have a certain part of your code which is very non-performant, which is acting very slow, and you have found out that it is because of cache misses, then yes, you would convert that part of the code into a more data-oriented design. You would implement data-oriented design into the more performance-critical part of your code, if you will, so that you can change the more performance-critical parts in order to get as much performance as possible from that, whereas still being able to modify the other things with the paradigm that you're used to and the ones that other people will be used to as well, right? So for a personal thing, if you want to get as much performance as possible, yes, take care of all data. If not, if you're working in a company which has already a design implemented and you have found out one thing is affecting this, then yeah, it's up to you. You decide on it. Polls?
No.
Okay.
Okay, now
Can we get used to? Can we remove stuff back? So that
only the host.
only the host.
Yeah.
Oh, we're on the host.
Yeah,
That is the host.
where's the
Alright.
Okay. Don't worry, bro. I
Um,
will take care of the tracking.
All right.
Okay.
Looking at the nature
Nature
of
of-
consecutive arrangement of the data for
Do design.
or the usage of SIMD instructions at consideration. SIMD is yes. So you would so if you're targeting SIMD, then you would organize your data for vector processing, right? So SIMDs are going to be done in VPUs, and to do that, you would organize your data for that. So it's not like it's a different argument. It's a different thing. So one doesn't like the other. So if you can do that for SIMD as well, but you can also do the same with object-oriented. You can have SIMD with object-orientedness. It's a different thing than the other. All right. Does ECS only limited on? Is it recommended for computing multiple objects doing complicated tasks? Yes.
Yes, it's
Yes.
That's the purpose.
Yes, very much. It is. The purpose is for computing multiple objects doing complicated tasks. No, we're showing simple tasks here so that you can wrap your head around like what's happening, what are component systems, what are entities. But yes, you can use for as complicated tasks as possible. That is its purpose, so that you can do complicated tasks as fast as possible on as many data as possible.
Untuk yang project terakhir tadi yang bentuknya game itu kan sebenarnya ada AI-nya untuk yang pesawat yang mau nabrak tanknya itu ya. Itu kan komputasinya itu AI.
So the thing is, the task you would be coding, that is algorithm, right? And like the complicated tasks means probably you're saying more complicated algorithms being used, right? So the algorithm is separate from data-oriented design. The algorithm you use, if you use good algorithm, it's going to be fast. If you use bad algorithm, it's going to be okay, decent, I guess, right? But I would say 90% of the performance you get from having good layout of data, and 10% is from good coding, from good algorithms, optimizing as much as possible the code part, the functions part, right? Data, multiple data. Okay, so we are with this one.
When should we use
DoD over OOP?
over OOP?
Especially if the game is already running smoothly, is there any benefit other than performance?
Reducing the cache miss.
Yeah, if the game is already running smoothly, then it's fine. I mean, if your game is already running smoothly, then don't, I guess. If you already have a game which has already used OOP to make a whole like large code base, you don't want to waste your time. You have to make educated decisions upon like when you would use DoD upon OOP. You know, so okay, I already have an object-oriented game which is a simple point-and-click game or simple platformer,
Which is okay.
Yeah, where I don't need many enemies and many entities in the game, many game objects in the game. Then yeah, go with it. Whatever you're used to, you want to get the product out as fast as you want. Then and you know object-oriented, you don't know data-oriented. Then do object-oriented. Make it, but you are limited. You have to know that you are limited to how many entities you can process and like stuff like that by OOP's inherent design. So if you want no shackles, if you want like uninterrupted as many entities as you want, then you would use DoD from the start. Depends on what you want.
Yeah.
Is the data layout in ECS data-oriented design predetermined and cannot be dynamically
It
created.
depends on the programmer, I think.
Yeah, it depends on implementation. So it depends on implementation. It is dynamically created, as in like, yeah, dynamically created as in you would allocate a heap, and the implementation could be in Unity, for example. In the backend, they have relational database system where the function would query the component that it requires, and the database will return in chunks all the components of all the entities that have all those components, and only those components it will return by having it as such, if that makes sense. So in that sense, yes, it can be dynamically created and allocated. And if you would think like moving data around a lot is very bad for performance, compared to cache misses, like in the book I read, Game Programming Patterns, Robert Nystrom, he said that even he thought moving data around a lot would be bad, but after doing that, like he got 50 times more performance by implementing this.
50 times.
Yes, in his example. Alright.
Apa versi Unity untuk development lebih baik pakai yang versi LTS atau versi latest? Kalau pengen nyoba EasyES itu saya sarankan menggunakan yang LTS ya. Karena ya lebih aman aja sih, ada supportnya, long term support, dan ya latest itu biasanya untuk beta doang, coba-coba ya.
Okay. So is ECS a design pattern? Is there any way to prepare an system before start coding stuff? Yes, ECS can also be a hybrid.
Design
You can,
pattern.
yeah, it can be used as a design pattern for when you're also doing object-oriented. Can you excuse me, please? So you saw in the example. Where's that example? All right. So just to make it more clear, I'm with hybrid. Oh, sorry. Yeah. Oh, but can you? I hope they can see this. Is it visible? Is this? All right. So you can see in this one. All right.
Yeah.
So you can see in this one. So you can see here we have components with. It's all like component out of components, and the data locality part you're making sure by doing this, by having just to one component and doing that update on all the component of one type before you move on to another, rather than doing instead of doing for every entity, you not. So instead of doing for int I equals 0, I is less than num entities I plus, and for every AI component, for every
Update.
AI, you would update. So if you would do this, and then instead of going for another entity, you would put this after AI component. So you would do the AI component update first, and then the physics component, and then the render component. That would be bad. That is a object-oriented pattern, which would be bad. But if you use the ECS pattern in OOP by doing this over here, then it is good. You can still get, you can still hit the cache. And if you want to, in your C++, if you want to measure how you would, if you want to know how you would measure cache misses, how you would profile that, there is a program called CacheGrind, which is from Valgrind. Oh, this is course. Sorry. You can use this, and it will give you, like, you can use this. You can run your program on this, and it will show how much is your cache miss rate, how many you like misses, and what's the one you require. I think. So I haven't personally. I wouldn't pretend that I have used this personally, but I can be used for doing that. Unity has its own debugger profile. I hope for measuring cache. I'm pretty sure they will have. So yeah, you can look into that. that helps.
Akan dirilis Gameloft ke depannya. Jadi untuk game yang ini maksudnya yang baru di development kan ya, itu memang dari aturan company sendiri kami nggak boleh ngomong ya. Surprise buat kalian. Jika game memiliki sedikit objek, apakah terlalu overkill dalam penggunaan ECS mengejar performatic? So, what if the objects are only few objects?
Only rendered objects?
For the objects used are only few.
Oh, only few.
Few numbers of them.
So it's like, so just think like where you would go, where you would want your program to reach. If you would later want your program to have a lot of entities, then you would now start implementing, you would now start to think about, like how are my caches being hit or missed, right? Like how are my caches being handled? But if you don't care at all, if you have designed your whole game and you're okay, I only need at most 10 entities in the game at a time and I want to code it as fast as possible, then okay, use object-oriented programming. It's fine. But there's a chance to learn how this would work and stuff, right? Even me, I'm not like a professional in entity component systems. I'm also learning as I'm going, right? And the only way to learn is by implementing it. And I have learned by implementing it, like single responsibility thing.
Close.
Yeah, single responsibility stuff. Yeah, I guess you can. I don't know. You need to do your own research on that because it's object oriented. It's a whole different thing. It has like Solid has its own design patterns, as far as I know. Solid consists of its own whole set of other design patterns, and ECS is another design pattern. So it has interfaces, templates, heavy use of object-oriented features, which ECS does not use. But if you want the hybrid system, then you can, I guess, but you would have to know. So for example, flyweight is a pattern that you could, of course, combine with ECS, right? But there are certain patterns which you could not. Probably command you can combine, but like a lot of patterns you can't, I'm sure, which are specific for where you would need interfaces and stuff like that. So yeah, I mean, hybrid as well. You can combine it, implement it yourself, find possibilities. Yeah, this is something that is not new, but at the same time also not so prevalent in programming communities. So it's really interesting. You do your research and you can implement your stuff and find answers. Yeah. That's the fun of programming, right? I think
it's all. That's all.
Yeah. All right. So I think we answered these. Wait, let me check in our group any
question.
Let me
Stop share. Maybe I will share the Visual Studio. It's working now.
Yes. You're welcome, Benny. You're welcome, Jonas. Welcome, everyone. Everyone was. Thanks, Judy.
Wait.
Visual Studio-nya atau
sebentar ya. Oke. Ini contoh dari Flex ya. Flex itu library ECS untuk C dan C++. Di sini bisa dilihat. Ini aku ambil dari GitHub-nya. Itu ada example yang bisa di-build dengan menggunakan CMake ya. Ada banyak example di sini. Kita bisa lihat contohnya untuk sorting. Sorting ada di mana tadi? Where is number 43? Sorting. Atau yang lainnya. Oke, ini contoh untuk sorting ya. Ada word di sini dan di sini kita perlu ngasih tahu yang jadi komponen itu apa. Dengan komponen adalah data. Nah, di sini yang jadi data adalah position. Position yang merupakan struct ya. Dia struct yang isinya cuma X sama Y. Nah, kita harus kasih simple menggunakan fungsi yang udah predefined, ECS komponen. Lalu kita buat beberapa entity di sini ya. Ya, ini ada beberapa entity 3, 1, 6, 2, 5, 4. Lalu nanti akan melakukan sort dengan pakai query ya. Di sini ada ECS query new word position. Jadi yang akan di query adalah komponen position. Nah, ini order by compare position. Ini akan nge-short positionnya. Ada banyak contoh di sini. Ini bisa dipakai di project kalian juga. Misalnya kalian punya project C++ dan butuh ECS, pakai flex saja, bisa. Mungkin aku open yang flexnya ya. Flex test. Ini bisa dilihat di sini juga. Ini flex. Ya, dia excellent. Nah, nanti ketika di build itu ada dynamic library, DLL outputnya, ada .lib juga, static library, dan itu bisa digunakan di project kalian. Nah, untuk implementasinya tinggal nyontek dari examples-nya aja, jadi gitu. Jadi ini udah otomatis nanti dia case friendly ya. Gitu. Cache friendly. Itu aja sih yang mau tak tunjukin. Thank you.
Okay.
Yeah, so before we end this, I would like to give you guys a bit of let me share this again. References of what helped me make these slides. I took a few slides from some people. So let me show you which ones those were so that you can go deeper and listen to the talks for a deeper idea of what this is. Share screen. Time for YouTube.
YouTube time.
No, I'll just give them
The reference.
the reference.
Okay.
Oh no, we can.
It's blocked by
Okay,
box.
I'll just tell you what to search for that. In the messages. Stop share. Okay.
Udah semua.
Search for Mike Acton talk on data. Design. Yeah, this one I have. Oh shit! Sorry. I send this privately. All right, to everyone. Yeah. So this is for Mike Acton's data oriented design talk. This was very helpful. You remember the part where I showed you guys the speed in which the L1 and 2 does. Yeah, that was from his talk. I took that from his talk. And general idea, the basic idea as well from his ECS. Unity's ECS was a very big help for like manuals and stuff. Robert Nystrom's talk. He has another talk. If you want to know, you can go to, I think, Rogue. Sorry. Celebrations. Search for ECS, and these are all YouTube talks basically. So you search in YouTube. In Rogue Celebrations is another channel which has I think 2 talks at least on ECS, and Robert Nystrom has the guy who wrote the game design pattern book. He has a talk about how he implements ECS, and this is specifically for like games